Hello. Not sure why my video isn't working, but I'm going with it. This lecture should be hopefully relatively short. Yeah, so on the back of talking about bandits and sort of the Markov decision process and introducing the reinforcement learning problem, let's now kind of introduce this concept of the Bellman equations, which some of you will probably find relatively familiar. Having done any kind of dynamic programming in the past, you should recognize a lot of these concepts. And actually, reinforcement learning in of itself is really a dynamic programming problem. If you really think about it, it's a sort of recursive problem. Kind of going back to the first lecture when I was discussing how this is fundamentally different than unsupervised or supervised machine learning techniques. In the context of a reinforcement learning task, you have an agent that is collecting data as it goes. And that's sort of one of the things that dynamic programming is very, very good at, right? At every respective time step, we then reevaluate the scenario. And given that we've taken this really large problem and split it up into smaller and smaller pieces, we can sort of evaluate what to do within each one of those pieces without having to think about solving the bigger problem on whole. So seen from that lens, you can kind of see that the decision made at a particular time step is a much, much smaller problem that has to be solved as compared to the larger problem. And if we solve the small problems correctly, then given an optimal solution there, we should also arrive at an optimal solution for the whole enchilada. So let's talk a little bit about that. And this is going to be a fun lecture that sort of formalizes a lot of these concepts more mathematically. So if you've seen this from a computer science standpoint, some of these equations may be a little bit scary, but really they distill down to this idea of recursion or dynamic programming. So first, let's talk about Richard Bellman. Richard Bellman, introduced this concept of dynamic programming back in 1953. He was an applied mathematician and had a really big impact, both in obviously in applied mathematics as well as computer science. And so the dynamic programming, just like we talked about just a second ago, takes a very large, complex, hairy problem and solves it by splitting it up into smaller and recursive subproblems that each individually can be solved more easily. And then if this is done correctly, will compound into a solution for the larger whole. You might have seen this in the context of recursive programming. You might have seen this with memoization. I wrote memorization. Of course, that's a terrific typo. I meant memoization, where, for example, calculating a Fibonacci sequence where the next value of the sequence is adding to the sum of all of the previous values. In fact, if you think about that Fibonacci example, that is literally what we're doing with reinforcement learning, right? At every step, we're adding and determining the future sum of rewards based on all the previous sum of rewards. So this is the general idea. So essentially just kind of hand waving aside, which you can't see because my video is off for some reason, this is just a way to solve a problem in a recursive fashion. So the Bellman equation is essentially a way to look at the expected discounts of a system given this recursive nature. So recall from the last lecture, and again, I've kind of linked both the Bellman equation Wikipedia article as well as Lillian Wang's blog, which is terrific. That really goes into depth on this subject as well. But you can find a lot of information about the Bellman equation all over. So let me know if you want more deeper explorations of this in the Discord. I'd be happy to kind of further explore these concepts. So again, remembering last lecture, recall that the value function of a particular state is defined as the expected rewards, or the expected future discounted rewards given that state. As here you can see that the return is defined. And we kind of touched on this in the last lecture when we talked about the value function being that, or actually when we talked about the state action function, being that ultimately, if we sort of take the value function here and we expand it out into this sort of by plugging in the value of the return, we can see that the value function can be represented as the expected value of the immediate reward we get plus gamma times the return of the next time step, which is simply the value function of the next time step. So we kind of redefine the value function of a particular state recursively in the expected value of the immediate reward plus a discount of the value function of the next state that we would see from that state. So if we know, for example, the probability, the transition model or a policy or what have you, we can then sort of determine this if we know we can figure out our value of our particular state if we know the value of the next state that we might be in. So you can kind of already see this recursive nature of this function. We can do the same thing for the Q for the state action function, right? Where we can see here that the state action function is the expected value of the reward seen in the next state plus this gamma of the gamma times the value function of the next state, kind of spread out more. Kind of if we want to sort of like evaluate this, we can see that as being the expected value of the next reward times the gamma times the expected value given the action, the expected value across the actions defined by our policy of the state action function. So again, we have this recursive definition here. Actually, I'm sorry that there might be a mistake in this slide where this is showing t plus 1. In this case, actually, it's just would be t. This is sort of like a bit of a nomenclature difference, I think. It can be seen as the current reward or the reward that we see in the next state, but fundamentally it's the same. It's just this idea that we have the definition of the value function being the expected value of the actions over the space of pi with q pi. So this is not in this particular slide, which I'll show you in a second, but we've seen this before where the value function is equivalent to the sum of every probability of actions times the value of taking that action given a respective state. So this is just another way to define the Q function. But you can kind of see that it's a recursive definition, meaning that the Q function is equivalent to the immediate reward of being in that new state plus all the possible values, the state action values of being in the next states that are possible from that point on, which is, I think, it's a little bit easier to see the dynamic nature here in the Q function than it is in the value function. In the value function, it's almost like this is a sequential thing. We're going to be in this state, and the next state, the next state. But in the Q function, we kind of see that we're going to be in this state, and we may be in a bunch of other states. And so we can kind of evaluate that. And if you've seen A star or Dijkstra's, that's exactly what's happening, right? You're in a particular node, and then you look at all of your neighboring nodes and add those kind of breadth-wise, and you kind of rinse, repeat. And it's exactly the same process here. So, like I mentioned, right, we can think about this, Q function definition recursively. And so at every state, we can now calculate the expected value of Q by looking at the next possible set of transitions. So kind of going back to here, defined more formally, the value function over a particular policy of a particular state S is the sum across all of the different policy actions, the distribution of actions times the state action value of being in that state and taking that particular action. And so then we can also define the Q value as being equivalent to the immediate reward in that particular state that we've just entered, given an action, plus the gamma of all of the various values of being in a future state. So you can kind of see, say we take a particular action, we get a particular reward as defined by this reward model RSA, and then from that point on, we can be in a variety of different potential states having taken that action. So this is the transition model. So say we take an action, we may or may not enter the state that we intend to enter, given this sort of transition model of our MDP. And so now we multiply this expected value because we may be in state 1 or state 2, right? And the value of state 1 is something, and the value of state 2 is another thing, and we want to take the sort of like average of those two. So that's what this sort of second half is saying about this Q function. And so if we take this Q function and we plug it into the value function, we get this term, this definition of the value function in terms of this transition function and the value function. And equivalently, we have this value function. We can also show, we plug that back into the Q function, and we get this other thing that we can again see is the Q function in terms of the next set of transitions. So you can sort of see one of the nice things about dynamic programming is like we could do this forever. And we actually will see exactly that in some of the algorithms that we define in the future. For example, policy gradient in particular, where we can demonstrate that we can improve a policy by taking its gradient. And you're like, what does that mean today? Don't worry about it. But that's the way, one of the ways that we can accomplish that proof, the ability that we can actually improve a policy just by taking a gradient, is by way of this sort of this eternal recursive expansion of this function. And you sort of, how would you do that? And I'll kind of skip ahead just a little bit by mentioning that, say your policy is a neural network. Now, if you can define it that way, where the output of a neural network is simply the action that you should take respective to a particular state that you're in, then now you can improve that policy just by way of stochastic gradient descent and all of the deep learning goodies that we've been talking about up until now. So yeah, this is sort of the bridge between sort of everything we've talking about and reinforcement learning. So yeah, you can kind of see this Bellman equation allows us for this recursive expansion and the definition and the sort of like flipping between the value and the state action function, which are kind of intimately related. So in a way, the way that this is sort of equivalent to updating this Q value function based on the expected values across each possible transition. So this is respective to the new state that we get, within a policy, and then the respective value from that point on. So kind of going back to this equation of the recursive definition of the Q state action function, we can see we get the immediate return given that state action pair. Then we have to look at all of the possible the transitions that we could possibly see, and then across that, all of the possible actions that we can take from that new state, and the then respective state action value from that state. We can do the same thing in the value domain, right? We can look at the value and then say, okay, across all possible actions, the immediate return that we get, plus all these the transition model times the value of being in that new model. And you can interoperate these two. You can obviously plop this thing into the Q function, but then you've got the Q function recursively defined as the value function, and we haven't really gotten very far there, which is kind of a problem. But either way, you can sort of now evaluate your policy by going through this thing where if I have a particular value for my policy, if I have a particular value for a state, right, I can then sample all of the different actions that I might take and then get those rewards that I may get. And I add to it this transition model and then multiply that by a value function that of the state that we have. And what's shown, and this is going to be kind of beyond the scope of this particular lecture, we'll talk about that in the next few lectures, but you can do this in a way such that this Bellman operator, you're operating on this function, this value function, will asymptotically approach the true value of the value function. Or really, one of the things that we kind of talk about in the context of the Bellman equation is that this operation, right, where say this iteration of calculating v pi the first time and then I do this again, say for a different set of states, the v pi of, this is the first iteration minus the v pi of the next iteration, the absolute value of that should be less than the next time that I operate on it. In other words, it's a contraction, that it's constantly getting better and eventually approaching asymptotically the true value. So This will be the sort of the subject of the lecture, the lecture after this one. And so once again, the idea here is we look at all the possible states, and then we apply the respective reward of the new state value per the transition probability of ending up in that state. So we'll take a look at that in the context of this sort of example that we saw in the last lecture, right? So let's say we start in this state of sleepy. We can look at all of the possible states from this point. We can go back to sleepy, right? In that case, we're going to see a reward of 1. Or we can go to this wake up state where we see a reward of -1. And so now if you do the calculation, the expected reward from here is going to be -1 plus 1. So our value is going to be, say that we have an equal probability of waking up or hitting snooze, that's going to be just 0. Our value of being in sleepy right now is 0. So now we kind of look at in a similar way, like breadth first search, the neighbors of sleepy is sleepy and wake up. And now we constantly update the value of being in that state based on the previous values of that state. So again, like say for example, we reevaluate the sleepy state. The sleepy state has a value of 0. We do the same thing, and we still get a value of 0 because 1 minus 1 is going to be 0. But let's take a look at a more interesting example, right? We're now in this state of wake up. In the state of wake up, the value is going to be equal to the value of sleepy plus this value of wake up. And the value of wake up is going to be determined by these possible -2 go to work and all the things that kind of go beyond it. And so now we can kind of see that the value of being in sleepy is -2 because our go to work, say our discount factor is 1. We've just added that. But I suppose given the sort of distribution here, right, of all actions, it's actually going to be -2 plus, well, yeah, no, it's just going to be -2 because these two rewards are constantly going to sort of cancel each other out. And so cool. So now our state of being in sleepy is going to be -2, and our value of being in state wake up is going to be also -2. And now you can kind of see how we just kind of constantly go down this path, and we're going to add 2 and 0.5, so 2.5 to this, and this is going to go back to sleepy, which is now going to be equivalent to 1.5 because we lost 1, and so on and so forth. And so that's the way that we kind of continuously expand on this in a breadth first fashion. We're constantly updating this these values, right, based on the likelihood of taking a particular action. So in this case, I'm assuming equal possibilities to just make the math a little bit simpler. But you can kind of imagine that if I'm more likely to wake up, like 0.9 versus 0.1 snooze, then the expected reward of hitting snooze is actually going to be only 0.1 because I'm only going to do that 10% of the time. So this is sort of the way that we can evaluate what the value of each state may be, so that we can maximize the potential returns, right? So you can actually maybe do this as an exercise for yourself and explore what kind of transition probabilities do we need here to ensure that we get to this termination state at all, because you can imagine getting into a particular sort of cadence here where you just go home and go to bed over and over and over again forever, because the way that these transition probabilities match out, and also the state transition probabilities, right? Like say I'm sleepy and I want to wake up, and I actually end up hitting snooze, right? This is a good example of a stochastic process, right? I'm most likely to wake up. I need to wake up, but I'm probably more likely to hit snooze, even though I employ the action of waking up, but I end up hitting snooze instead. So what kind of policy, kind of stochastic policy distribution, and what kind of transition distribution do you need to actually hit the termination state versus just sort of ending up in this infinite loop of going home and going to bed and hitting snooze or waking up forever. As you can kind of see, there are other sub paths here, such as calling in sick and then going to bed, and then this loop in particular, right, this -1, 0, 5 has this expected value of 4, and if you do this forever and ever and ever, you eventually, will get old and never actually go to work. And so this is not a very realistic state diagram, but you can kind of imagine how this would get applied to a more general purpose environment. So yeah, this is sort of the introduction to the Bellman equations and also the tabular MDP scenario. And so in the next lectures, we'll talk about the approaches to the tabular reinforcement learning, such as how do we actually evaluate the value of a policy, how do we iterate on the value function, how do we iterate on a policy, and then how do we start to kind of think about that in terms of doing this for more complex MDP, such as a continuous state space or something like that. Cool. See you next time.